So in terms of a practical discussion about how infrared spectroscopy works, let's focus on a hydroxide group. So with something like silicon dioxide, there's OH groups present on the surface, and these typically absorb a wavelength of about 3600 wave number, inverse centimeters. So what happens when we take this measurement? What we're going to do is that we have some infrared source, and we're going to send our sample, our light source, through a splitter. One's going to go to a detector that's used to determine this intensity of the light coming to the sample. The other one's going to pass light through the sample, and then it's going to measure the intensity that comes out the other side. So the raw data is what's called the transmission data. What we're looking at is basically the signal intensity on D1 over D2, detector 1 over detector 2. Now, if we are not at the frequency at which this OH group vibrates, it doesn't absorb. They don't resonate. So that's what we're doing with infrared, is we're looking for where the bond resonates and absorbs. So nothing's going to happen for a while, and then all of a sudden when we get to 3600, we're going to see a dip. And we're going to see a dip because the OH group is absorbing this light now. We're no longer seeing 100% transmission. Now, this absorption is not exactly at 3600, and there's a lot of reasons for this. There is a theoretical limit on how tightly we can measure that absorbance, and that goes back to Heisenberg uncertainty. Because this wavelength does correspond to an energy, and these electrons are absorbing this energy in the vibrations. So if we had an infinite spike, a Dirac delta function that said, oh, it only absorbed at this frequency, we would know the energy of the electron with 100% precision. We can't know that. So the best we can do is what's called a Lorentzian shaped absorption curve. So there's going to be a frequency, it's going to absorb in a range of frequencies that correspond to the Heisenberg uncertainty. Now, the peak is going to be at 3600, which corresponds to this. But above and below it, we'll still see some absorption because the electron's energy levels aren't precisely defined. Now, once we get away from it, we'll go back to 100% transmission. Now, this is a very glorified, simplified molecule. Typically, when we do this with a sample, we measure a whole bunch of things. So we're going to see something corresponding to each functional group. Now, that said, IR can be reported both in terms of transmission as well as absorbance. And you'll see it reported both ways. The thing is, you're looking for a peak. Now, my understanding or experience is organic chemists like to work in transmission, which makes sense. They were the first ones to really implement this technique on a large scale. But to go to the absorbance, it's just the log. So, associated absorbance spectrum, A here, it looks something like this. It's going to take basically an inverse picture. Both will work. Whatever you want to work with, absorbance versus transmission, is fine. Be able to work at both, but understand that if you see a dip in transmission, it's just a spike in absorbance. They both correspond to the molecule having a functional group associated with that particular vibrational mode. And we can go to tables, look up what functional groups we expect to be there, and based on the shapes, we can also resolve between ones that may have similar vibrational modes.